Empty space, you have always been told, is nothing at all, a blank, the gap that is left over when everything else is taken away. But here is what they left out. That emptiness is not empty, and it may not even be finished. The space around you right now is soaked in an invisible field, holding a single steady value everywhere, and that value is the only reason your atoms hold together at all. Physicists can actually calculate whether that value rests at the true bottom of reality, or merely in a shallow hollow with somewhere deeper waiting below it. In the year 2012, a measurement at the largest machine ever built quietly pointed to the second answer. Our universe may be balanced on an edge that no one can explain, a single quantum accident away from rewriting itself completely, without warning, at the speed of light. Get comfortable and let your breathing slow. Hit subscribe if you're new here. Because by the end of this, the solid ground you have trusted your whole life will feel like something far thinner and far stranger than you ever supposed. Now, let's slowly ease into this. Part 1. The 4 endings and the one with no date. Every story you have ever been told about the end of the universe comes with a calendar. That is the first thing worth noticing, and almost nobody notices it. When physicists describe how everything finishes, they hand you a date, or at least a range of dates, and the date is always so far away that it stops meaning anything. The end of the world, in the language of cosmology, is never tonight. It is always a number so large that your mind slides off it. Consider the version most people have heard, the slow one. In that ending, the stars finish burning. Not all at once, but over a length of time that makes the entire history of life on Earth look like a single breath. The smallest, dimmest stars, the red dwarfs that sip their fuel instead of gulping it, will still be glowing faintly when the cosmos is hundreds of times older than it is now. After that comes the long dark, where the only light is the occasional flare of matter falling together, and then even that fades. Galaxies cool, black holes swell, swallow what is left, and then, across spans of time written as 10 followed by 100 zeros, they too evaporate into a thin haze of radiation. The universe does not explode at the end of this story. It simply runs down, like a clock nobody winds, until there is nothing left that can change. We call it the heat death, or the big freeze, and the thing to hold on to is that it takes essentially forever to arrive. There are other endings on the menu, and each one also comes stamped with a faraway date. In one, the expansion of space reverses, and everything that flew apart comes crashing back together into a single dense point, a mirror image of the beginning. That is the big crunch, and even in the models where it happens, it is billions upon billions of years out. In another, the expansion does not slow down but speeds up without limit, until it tears galaxies apart, then solar systems, then atoms, then the structure of space itself. That one is called the Big Rip, and the most aggressive estimates still place it tens of billions of years from now. 3 endings, 3 calendars, and all 3 of them share the same quiet comfort. You can see them coming. There is a road that leads to each one, a sequence of warning signs stretched across time so long that no living thing will ever feel the approach. I want you to sit with that comfort for a moment, because we are about to take it away. The reason all of these endings feel survivable, in a strange emotional sense, is that they are scheduled. A scheduled ending is one you can prepare for, in principle. It is one you can watch arrive. It is one that obeys the ordinary rule we trust without ever stating it out loud, the rule that says big things give you warning, that the world announces itself before it changes, that you will at least know. There is a 4th ending. It does not appear on the calendar at all. It has no date, no countdown, no road of warning signs leading up to it. It could be 10 to the 100th power years away, which is to say almost unimaginably distant, and it could also, in principle, begin in the next second, in this room, without a single sign that anything was about to happen. Both of those statements are true at the same time, and learning how they can both be true is the entire reason you are here tonight. This 4th ending does not come from the stars burning out, or from space tearing, or from gravity pulling everything back home. It comes from something far stranger and far quieter. It comes from the possibility that empty space, the one thing in all of physics that we treat as permanent, as the unchanging stage on which every other event plays out, might not be permanent at all. It might be resting. It might be holding a shape that only looks final, the way a ball resting partway down a hill can look perfectly still right up until the moment it isn't. Physicists have a name for this fourth ending. They call it vacuum decay, and it is sometimes described, with a kind of grim affection, as the quietest apocalypse in all of science. I want to use that phrase carefully tonight, because it is going to come back, and its meaning is going to change by the end. For now, hold it loosely. The quietest apocalypse, an ending so silent that, if it ever came, no one would hear it, no one would see it, and in a sense I will try to make precise later, no one could ever even know it had happened. The first thing to understand is that this is not fringe science, and it is not a thought experiment somebody invented to frighten people. The mathematics behind vacuum decay was worked out almost 50 years ago by some of the most respected physicists of the 20th century, and it is taught in graduate courses today. More than that, a measurement made at the largest scientific machine ever built, finished in the year 2012, quietly suggested that our universe may actually be in exactly the precarious state this theory describes. We did not just imagine the unstable vacuum. We measured two numbers, and the numbers pointed straight at it. So this is the journey I want to take with you. We are going to start with a simple question that turns out to have a deeply unsettling answer. The question of whether empty space is truly empty and truly finished. We are going to follow the physicists who first wrote down how a universe like ours could quietly rewrite itself, and we are going to meet the moment, on a summer day in 2012, when a measurement turned an abstract worry into something with our address on it. Then we're going to look directly at the thing itself, the bubble that could erase everything at the speed of light, and we are going to ask the two questions that matter most. Could anything cause it? And could it already be on its way? I should tell you now, before we begin, that this is not a story designed to keep you awake at night with fear. It is very nearly the opposite. The deeper we go, the clearer it becomes that this particular ending, alone among all the others, is one you could never experience as an ending at all. There would be no terror, because there would be no time in which to feel terror. The thing that makes vacuum decay sound like the most frightening idea in physics is the very thing that, looked at honestly, drains the fear out of it. What is left, once the fear is gone, is something quieter and far more interesting. A kind of vertigo about how much of reality we ever took for granted. But to get there, we have to start with the ground under your feet, and the ground under everything, the part of the universe you have never once worried about because it has never given you a reason to. You have spent your entire life standing on the assumption that empty space is the most reliable thing there is. Tonight I want to gently pull on that assumption and show you what it is actually attached to. Because the universe, as it turns out, may be balanced on something far thinner than solid ground. And the strangest part is not that this balance exists. The strangest part is that we can measure how close to the edge we are sitting, and the answer that comes back is so finely poised, so close to the line between safe forever and not safe at all, that the physicists who calculated it could only describe our universe with a single phrase. They said we are living on the edge. Before this is over, I want you to understand exactly what edge they meant, and why nobody can yet explain why we are perched on it. It is worth saying clearly, before we go any further, that this is not a fringe idea dressed up to sound respectable. It sits squarely inside mainstream physics, in the same body of theory that successfully predicted the particles found at the world's great laboratories, and that underlies the technology you use every day. The people who first worked it out were not doom prophets. They were among the most careful and celebrated physicists of their century, the kind whose names appear on the equations students still learn. And the unsettling hint that our own universe might be in the precarious state the theory describes did not come from speculation, but from a measurement, one of the most expensive and meticulous measurements ever made. So as strange as the next 2 hours may sound, I want you to hold it as real science, not as a story told to frighten. The strangeness is not a flaw in the telling, it is a property of the world, so settle in and let your shoulders drop and let the ordinary solidity of the world soften just a little. We're going to talk about the flaw beneath reality and the long, patient question of whether it is truly the bottom or only the higher step of a staircase we have never been able to see. Part 2. Empty space is not empty and may not be finished. Let us begin with a word you use all the time without ever inspecting it. The word is empty. When you imagine empty space, the gap between the stars, the room inside a sealed jar with the air pumped out, You probably picture nothing at all. A blank, an absence, the stage with no actors on it. For most of human history, that picture was good enough, and even today it is the picture almost everyone carries. But it is wrong, and the way it is wrong is the doorway into everything that follows tonight. In modern physics, empty space is not a blank. It is a thing, with properties, with structure, and with a particular amount of energy that is not zero. The reason for this is that the universe is not really made of particles floating in a void. It is made of fields, which are a stranger and more fundamental idea. A field is something that has a value at every point in space, everywhere, all the time. The most familiar example is the magnetic field around a magnet, the invisible influence you can feel when two magnets push or pull at a distance. Physics tells us that everything is like that, underneath. There is a field for the electron, a field for light, a field for every kind of particle that exists. What you call a particle is really just a ripple, a disturbance, a little packet of energy in one of these fields. Among all of these fields, there is one that matters most for our story, and it has a name you have almost certainly heard. It is the Higgs field, and it fills all of space, including the space you think of as completely empty. The Higgs field is the reason many particles have mass at all. As particles move through it, they interact with it, and that interaction is what gives them their heft, their resistance to being pushed. Without the Higgs field switched on the way it is, the building blocks of matter would behave entirely differently, and the ordinary world, atoms and chemistry and you would not be possible. The crucial point is this: the emptiness around you is not empty. It is soaked in the Higgs field, quietly holding a particular value everywhere, and that value is part of what makes reality work the way it does. Now here is where the question sharpens. When physicists say a region of space is a vacuum, they do not simply mean it has no particles in it. They mean something more precise. They mean it is in its lowest possible energy state. The vacuum is the configuration the fields settle into when there is nothing left to give up, no more energy to shed, the bottom of the bucket. And for a very long time, everyone assumed that our vacuum, the state our fields are resting in right now, was exactly that, the true bottom, the final, lowest, most settled condition that space can be in. But there is a way for that assumption to be wrong, and to see it, I want you to picture something simple. Picture a single ball, and picture the ground it rests on, but make the ground uneven, with valleys and rises, like a stretch of hilly country drawn as a smooth curve. The ball wants to roll downhill toward lower ground because that is what things with energy do. They shed it, they settle. If you place the ball in a valley, it rolls to the bottom of that valley and stops, and there it sits, perfectly still, perfectly stable. Nudge it gently and it rolls right back to the lowest point. It looks, for all the world, like it has found the bottom. Here is the trap. The bottom of a valley is only the lowest point nearby. It is not necessarily the lowest point anywhere. Imagine that just over the next rise, hidden from the ball's little world, there is a second valley, and the floor of that second valley is lower than the first. The ball cannot see it. The ball has no way to know it is there. As far as the ball is concerned, it has reached the end of all downhill, the final resting place, the true bottom. But it has not. It has only found a local bottom, a comfortable hollow that happens to be surrounded by higher ground on every visible side. The deeper valley is still out there, separated by a hill the ball would have to climb before it could ever roll down the far side. Physicists have names for these two situations. A ball resting in the true lowest valley, the deepest one anywhere, sits in what they call the true vacuum. A ball resting in a hollow that only looks like the bottom, with a deeper valley hidden beyond a rise, sits in what they call a false vacuum. And the entire weight of tonight's question comes down to a single sentence. We do not know, for certain, which kind of vacuum our universe is sitting in. We do not know whether the value the Higgs field is holding everywhere, the value that lets you exist, is the true bottom of everything, or only a comfortable hollow with a deeper one waiting on the far side of a hill we cannot see. That phrase is going to follow us through the rest of this, so let me say it plainly and let it settle. For all of recorded history, we may have mistaken the valley floor for the bottom of everything. We looked at empty space, we found it stable, we nudged it in 1,000 experiments and it always rolled back to the same place, and we concluded it was final. But stability against a small nudge is exactly what a false vacuum looks like. A ball in the higher valley is perfectly stable against anything that only pushes it a little. It would take a real climb, all the way up and over the dividing hill, to discover that there was ever anywhere lower to go. You might reasonably object at this point. If our vacuum is sitting in a hollow and there is a deeper valley beyond a hill, then surely we are safe, because the ball cannot climb the hill on its own. A ball does not spontaneously roll uphill, and in the ordinary everyday world you would be completely right. But the universe is not ordinary at the smallest scales. It is quantum, and quantum things do not obey the rule that says you must go over a hill to get to the other side. They can go through it. This is one of the genuinely strange facts of nature, confirmed in countless experiments, and it has a name. It is called quantum tunneling. In the quantum world, a particle facing a barrier it does not have the energy to climb has, nonetheless, a small but real chance of simply appearing on the other side, as if it had passed straight through the wall without ever going over the top. This is not a metaphor, and it is not a trick of language. It is how the sun shines, because the particles fusing in its core tunnel through barriers they could not otherwise cross. It is how certain electronics work. Tunneling is real, it is measured, and it means that a barrier in the quantum world is never a perfect guarantee. It is only a probability, a chance that the thing on the wrong side stays where it is. Now bring those two ideas together and feel the floor tilt. If our vacuum is a false vacuum, a ball resting in a higher valley, then the dividing hill between us and the deeper valley is not a wall. It is a barrier that quantum physics can tunnel through. Somewhere, sometime, in some small region of space, the fields can tunnel from our hollow into the deeper valley beyond, the way a particle tunnels through a wall it could never climb. They do not have to climb the hill, they only have to, by pure quantum chance, find themselves on the other side of it. And when that happens, when even a single microscopic patch of space slips from our vacuum into the lower one, something begins. That patch is now in a different state than everything around it. It is, in a sense, a small piece of a different universe, with different rules, surrounded by the old one. What it does next, how it grows, how fast it spreads, and what it does to everything in its path, is the part of this story that turns from a curiosity into the quietest and most total ending physics has ever described. It is worth pausing to feel how counterintuitive this whole frame really is, because everything in your daily experience pushes against it. When you empty a glass, you think you have removed everything from it, but you have only removed the air. The space that remains is still full of fields holding their values, still soaked in the Higgs field, still carrying its own quiet energy. There is no way to empty that out. You cannot pour the vacuum away. It is not a container that can be made truly hollow. It is the deepest layer of the world, the thing that is left when everything else is taken away, and it has a state, a condition, a value it is holding, just as surely as a stretched spring holds tension or a still pond holds a level. We have simply never had occasion to notice, because in all of human history that level has never once changed. The reason it has never changed is the reason the word metastable matters so much, and I want to make sure it has fully landed before we move on. A truly stable thing is at the bottom of everything, and nothing can take it lower. A metastable thing looks exactly like a stable thing from the inside, behaves exactly like one in every ordinary test, and yet is not at the true bottom. The two are indistinguishable by any gentle experiment, because the difference between them only shows up when something crosses the hill to the deeper valley, and crossing the hill is precisely what almost never happens. This is why we could go 13.8 billion years, run every experiment we could devise, and never once catch our vacuum misbehaving. A metastable vacuum is not a vacuum that wobbles or flickers or gives warning signs. It is one that sits perfectly still, perfectly convincing, holding its value with total steadiness, while a deeper possibility waits, silent and patient, on the far side of a barrier almost nothing ever crosses. But before we follow that patch and watch what it becomes, I want to be fair to the comfort we started with, and I want you to keep breathing easily. Nothing I have said yet means this is likely, or soon, or anything you need to fear. It only means it is possible, that the door exists. For decades, the false vacuum was a what-if, a line of mathematics with no clear connection to the real numbers of our universe. The question of whether we actually live in a hollow or at the true bottom stayed open and abstract. What changed? What dragged this idea out of the realm of speculation and gave it a measurement and a face? Happened first as pure theory in the 1970s, in the work of a physicist who decided to ask exactly how a false vacuum would die. And that is where we go next. Part 3. Coleman writes down how a vacuum dies. In the 1970s, a physicist at Harvard named Sidney Coleman sat down to answer a question that sounds almost reckless when you say it out loud. He wanted to know what would happen, in precise mathematical detail, if the vacuum of the universe were false. Not whether it was false, which nobody could yet say, but what the consequences would be if it were. He wanted the equations for the death of empty space, and in a pair of papers published in 1977, one of them written with his colleague Curtis Callan, he found them. Coleman was, by every account, one of the clearest thinkers of his generation, a physicist other physicists went to when they wanted something explained properly. His lectures were famous. His habit was to take an idea that seemed mystical or frightening and reduce it to something you could actually calculate, something with edges you could hold. So when he turned to the fate of the false vacuum, he was not trying to write a horror story. He was trying to do what he always did, which was to make a vague unease into a sharp, honest equation. The title he chose for the work was almost dry. He called it The Fate of the False Vacuum. There was no exclamation mark. There did not need to be. What Coleman worked out is, at its core, the story I have already started telling you, but made rigorous. He showed that a false vacuum does not decay all at once, everywhere, in a single flash. That is not how it works, and understanding why is important. Instead, the decay begins in one tiny place. Somewhere in the immense expanse of space, by quantum tunneling, a single small region slips from the false vacuum into the true one. This little region is a bubble. Inside it, the fields hold the new, lower value. Outside it, everything continues as before, and in the first instant of its life, this bubble faces a kind of decision, written into the mathematics, between two fates. The decision comes from a competition between two effects, and Coleman made the competition exact. On one side, there is the inside of the bubble, which is at lower energy than the surroundings, and that energy difference wants to make the bubble grow, because growing converts more of the high-energy false vacuum into low-energy true vacuum, and nature favours shedding energy. On the other side, there is the wall of the bubble, the thin shell where the fields are caught in transition between the two values, and that wall costs energy to maintain. A small bubble is almost all wall and very little interior, so for a tiny bubble the cost of the wall wins, and the bubble collapses back into nothing, healing over as if it had never formed. Most tunneling attempts end exactly this way, snuffed out before they begin. But there is a threshold. Coleman calculated the precise size a bubble must reach for the balance to tip the other way. If a bubble manages to tunnel into existence already larger than this critical size, then the energy gained by its growing interior overwhelms the cost of its wall, and from that moment on, growth feeds growth. The bigger it gets, the more strongly it wants to get bigger. It crosses over from a fragile flicker that wants to vanish into an unstoppable expansion that wants to consume. Physicists call the mathematical object describing this threshold moment the bounce, a beautiful and slightly eerie name for the solution that sits exactly at the tipping point between collapse and runaway. I want to slow down on what Coleman's equation said happens after the bubble crosses that threshold, because this is the part that turns the abstract into the unforgettable. Once a bubble is past the critical size, its wall begins to move outward, and it does not move gently. The same energy difference that drives the growth pours into the wall as motion. And because the wall is, in effect, weightless in the relevant sense, there is almost nothing to stop it accelerating. Within a vanishingly short time, the wall is moving outward at very nearly the speed of light. Not a fraction of it, nearly all of it, the fastest thing the universe permits. Picture what that means as a shape. You have an expanding sphere of true vacuum, a region where the rules are different, and its surface is racing outward in every direction at almost the speed of light. It does not slow down. There is no friction to slow it, no fuel to run out of, nothing in ordinary matter that can resist it. A star in its path does not block it. A galaxy does not block it. The wall passes through everything, and as it passes, it converts the space it crosses and everything occupying that space into the new state. The sphere just keeps growing, swallowing more volume every second, and because it grows at light speed, the volume it consumes increases without limit. There is a detail here that I do not want you to miss, because it is the seed of the strangest idea in this entire story, and I will plant it now and return to it later. The wall moves at essentially the speed of light. Light is also, of course, the thing that carries information, that lets you see anything at all. Nothing can travel faster than light, which means nothing can outrun this wall and nothing can announce its approach ahead of it, because any warning would itself have to travel at or below the speed of light, and the wall is already moving at that speed. The wall and any possible signal of the wall arrive at the same instant. Hold that. We will need it. What did Coleman himself make of all this? He was by temperament more amused than terrified, in the way that certain physicists are when they confront something enormous and impersonal. He understood that he had written down the equations for a catastrophe with no equal, an event that would not destroy a planet or a star or a galaxy, but rewrite the rules of existence across an ever-growing region of the cosmos. And yet his papers are calm, careful, almost playful in places. He was describing a possibility, a piece of how the world might be built, and the calm came from the same place all good physics comes from, the conviction that understanding a thing clearly is better than fearing it vaguely. There is something worth lingering on in the way Coleman approached this, because it tells you a great deal about how physics actually confronts the unthinkable. He did not treat the death of the vacuum as a thing to be feared or sensationalized. He treated it as a problem to be solved, with the same tools you would bring to any other question, the mathematics of how systems shed energy and settle into lower states. The bounce solution he found is, to physicists, a thing of real elegance. It describes the most probable way for the tunneling to happen, the path of least resistance through the barrier, the exact configuration a bubble must have at the instant of its birth to sit balanced between collapsing and growing. From that single object, you can calculate everything that matters, including the one number that decides our fate in practice, which is how often, on average, such a bubble manages to form in a given amount of space and time. Coleman turned a vague dread into a quantity you could compute, and that is, in its way, a deeply calming act, even when the quantity it points to is enormous. I also want you to hold on to the physical meaning of that critical size, because it is the quiet hinge on which everything turns. A bubble smaller than the threshold is dominated by its wall, and the wall costs more energy than the small interior can repay, so the bubble is, in effect, a bad bargain that the universe immediately undoes. It flickers into being and is gone, healed over, leaving no trace. The overwhelming majority of tunneling attempts are exactly this, false starts that erase themselves in an instant. Only a bubble that happens to tunnel into existence already past the threshold, already large enough that its growing interior can pay for its wall and more, survives to become the runaway. This is part of why the whole process is so rare. It is not enough for the fields to tunnel. They must tunnel into a configuration large enough to live, and that is a far steeper demand, which is part of what pushes the expected waiting time out to the staggering numbers we will reach later. The vacuum is not protected by a wall that cannot be crossed. It is protected by how unlikely it is to be crossed in just the right way. But here is what Coleman's 1977 work did not yet include, and it is a glaring omission once you notice it. His first calculation treated the bubble and its expansion without bringing in gravity. He worked out how a false vacuum decays in a universe where you ignore the way energy bends space and time. That is a reasonable place to start, the way you might first study a falling ball while ignoring the air. But gravity is not a small effect when you're talking about the energy of empty space itself and the structure of the cosmos. Gravity is woven into the vacuum, and when Coleman, a few years later, joined forces with another physicist to put gravity back into the equations, the picture did not get gentler. It got worse. The bubble, it turned out, was not just an expanding region with different rules. Under gravity, its interior could do something far more final than merely change the laws. It could collapse. And that is the calculation we turn to next, the one that took the death of the vacuum from a strange rewriting into something closer to annihilation. Part 4. Gravity Makes It Worse. In 1980, Sidney Coleman returned to the false vacuum, this time with a collaborator named Frank DeLucia, and together they did the thing the first calculation had set aside. They put gravity in. Their paper has a title that sounds almost bureaucratic, Gravitational Effects on and of Vacuum Decay, but inside it is one of the more sobering results in theoretical physics, and it changed the character of the whole idea. To understand what they found, you have to remember a fact about gravity that Einstein gave us, and that we still do not fully feel in our bones. Gravity is not really a force pulling objects together, it is the bending of space and time by energy. Anything that carries energy curves the space around it, and that curvature is what we experience as gravity. The Earth curves space, and you feel that curvature as your weight. Now, the vacuum itself carries energy. Empty space has an energy of its own, the energy of those fields holding their values everywhere. And that means the vacuum's energy too bends space and time. The shape of the cosmos depends on it. So when a bubble of true vacuum forms, you're not simply swapping one set of rules for another inside an expanding sphere. You're changing the energy of the vacuum in that region, and therefore you're changing how space and time are curved there. Coleman and DeLucia worked out the consequences, and the consequences depend on something we cannot measure in advance, which is the energy of the true vacuum compared to our own. There were a few possibilities, and the one that nature most likely hands us is the grim one. In the case they paid the most attention to, the true vacuum, the deeper valley, has a lower energy than ours by a large amount, and in particular it has what is called a negative energy density. When that is the case, the inside of the bubble is not a calm new region where chemistry simply works differently. The interior is a place where space and time curve so violently inward that the region collapses. It falls in on itself and ends in a singularity, the same kind of runaway crushing that lies at the center of a black hole. The bubble, in other words, does not give birth to a new and habitable cosmos. From the point of view of anything caught inside, it is a trapdoor that opens onto total gravitational collapse. Let me put the two pieces of the picture side by side, because together they are far heavier than either alone. From Coleman's first calculation, we have a wall of true vacuum racing outward at nearly the speed of light, converting everything it touches. From the Coleman and DeLucia result, we learn that the region it leaves behind, the inside of the bubble, is not a survivable place at all, but a pocket of collapsing space heading for a singularity. So the wall sweeps over you. The rules that allow your atoms to exist are rewritten in the instant of passing, and the space you occupied is, moments later in its own internal reckoning, crushing itself out of existence. There is no version of this in which something on the inside endures. It is not a transformation you could ride out. It is an erasure followed by a collapse. I said at the start that we would take away the comforting feeling that comes with a scheduled ending, and this is the part where the temperature first drops. Every other ending of the universe leaves something. The heat death leaves a thin, cold haze that at least obeys the same physics you do. The big crunch, if it happened, would at least be made of the matter you know, compressed but recognizable in kind. Vacuum decay leaves nothing of the old order at all. It does not rearrange the furniture of reality. It replaces the room, and the new room cannot hold furniture, and then the new room falls in. Of all the ways the cosmos could end, this is the only one that is total in this particular sense, that erases not just the things in the universe, but the conditions that made those things possible. And yet, I want to keep us honest, because honesty is the only thing that makes this bearable, and frankly, the only thing that makes it interesting rather than merely lurid. Everything I have just described is a consequence of an if our vacuum is false, if the true vacuum lies lower by the right amount, if the energy of that deeper valley is negative, as the most studied case assumes. Coleman and DeLucia did not prove that our universe is doomed. They proved something more careful, and in a way, more remarkable. They proved that the death of a false vacuum is a clean, calculable, lawful event, that you can write down its mathematics with the same confidence you write down the orbit of a planet. They took a nightmare and made it a theorem. Whether the theorem applies to us was, in 1980, still completely unknown. That distinction matters enormously, so let me dwell on it for a moment before we move forward. There is a difference between a thing being possible according to the laws of physics and a thing actually being the case in our particular universe. The laws permit a great many catastrophes that simply are not loaded into the world we live in. For all that the 1980 calculation revealed, the false vacuum might have been a mathematical curiosity, a description of how some other universe could die, with no bearing on ours. To connect the theory to reality, you would need to know the actual shape of the energy of the actual Higgs field. You would need to measure the real numbers, the ones that tell you whether our valley is the true bottom or merely a hollow. And in 1980, those numbers were out of reach. The particles whose masses encode the answer had not all been found. The machine that could weigh them had not been built. So for roughly the next 3 decades, vacuum decay lived in a strange middle country. It was respectable, it was rigorous, it was in the textbooks, and it was, as far as anyone could say, possibly irrelevant to us, a beautifully worked out account of a danger that might belong to some other cosmos entirely. Physicists would mention it, calculate with it, use it to think about the early universe, and then set it down, because there was no way to tell whether the door it described was a door in our house or in a house we would never visit. It helps to see why gravity tilts the outcome toward collapse rather than toward a gentle new world, because the instinct is to imagine the inside of the bubble as simply a different place, perhaps strange but survivable. The mathematics does not allow that comfort in the most likely case. The energy of a vacuum is not just a number sitting quietly in the background. It actively shapes space and time. A vacuum with positive energy makes space want to fly apart, expanding. A vacuum with negative energy makes space want to fall together, contracting. And the deeper valley, the true vacuum that lies below ours, is most naturally a place of negative energy, because it sits so far down the curve. So the interior of the bubble is not a calm room with different furniture. It is a region where space itself has been told to collapse, and it obeys, folding inward toward the same kind of crushing singularity found at the center of a black hole. The bubble wall converts the rules, and then the converted region, under its own changed gravity, falls in on itself. This is the point where I think it helps to name plainly what would and would not survive, so the imagination has somewhere honest to rest. Nothing made of ordinary matter survives the passing of the wall, because the masses and forces that hold ordinary matter together are exactly what the wall changes. A proton is a delicate balance of particles and forces, and that balance depends on the Higgs value being what it is. Shift it, and the proton is no longer a proton, the atom is no longer an atom, the molecule, the cell, the star, none of it can hold its shape. And then, moments later in the bubble's own internal time, the gravity finishes what the wall began, drawing the converted region down toward collapse. So when physicists say vacuum decay would be total, they do not mean it would kill everything in the ordinary sense the way an explosion kills. They mean it would remove the conditions under which the word everything has any reference at all. It is less like destruction, and more like an erasure of the page the destruction would have been written on. What ended that long suspension was not a new idea. It was a measurement. It was the completion of a machine 27 kilometers around, buried beneath the border of 2 countries, built to do many things, but able, almost as a side effect, to weigh the 2 particles whose masses would finally tell us which kind of valley we live in. When that machine delivered its most famous result, on a summer day in 2012, it did not announce that the universe was ending. It announced the discovery of a single particle. But hidden inside that discovery, once you combined it with what we already knew, was the answer to Coleman's old question, and the answer was not the comfortable one. The answer was that we appear to be living in exactly the kind of valley that has a deeper one waiting beyond the hill. To see how a triumphant discovery quietly delivered such an unsettling verdict, we have to go to Geneva, to the 4th of July 2012. Part 5. The Measurement That Made It Personal. On the 4th of July 2012, in an auditorium at the European Laboratory for Particle Physics near Geneva, 2 teams of scientists announced that they had found the Higgs boson. The room was full of people who had spent decades of their lives chasing this single result. There was applause, and there were tears, and one elderly man in the audience, the physicist Peter Higgs, who had predicted the particle nearly 50 years earlier, wiped his eyes. It was, by any measure, one of the great days in the history of science. Nothing about the announcement mentioned the end of the universe. It was a celebration of a beginning, the completion of a picture of matter that physicists had been assembling for a century. To understand why this triumphant day quietly carried such a heavy verdict, you have to understand what the Higgs boson actually is and why finding it mattered so much. Earlier, I told you about the Higgs field, the thing that fills all of space and gives particles their mass. A field like that, in quantum physics, always comes with a particle attached to it, a ripple in the field that you can, in principle, knock loose if you hit the field hard enough in a small enough place. The Higgs boson is that ripple. Finding it was the way to prove the field was really there. It was the difference between believing in the ocean and finally catching a single wave in your hands. The machine that did the hitting was the Large Hadron Collider, a ring 27 kilometers around, in which protons are accelerated to nearly the speed of light and smashed together, concentrating enormous energy into a tiny point, occasionally enough to shake a Higgs boson loose for the briefest of moments. When the 2 experiments weighed the particle they had found, they got a mass of about 125 times the natural unit physicists use for these things, a unit called the giga-electron-volt. You do not need to feel the unit. You only need to hold the number, 125, because it is one of the 2 numbers that decide our story. The other number was already known, and it belongs to a different particle, the top quark, the heaviest of all the known elementary particles, which weighs in at about 173 in those same units. 125 for the Higgs, 173 for the top quark. Two numbers, freshly pinned down, and together they are enough to answer Sidney Coleman's old question about which kind of valley we live in. Here is how two particle masses can possibly tell you about the fate of empty space, because at first the connection seems impossible. It comes through the shape of the Higgs field's energy, the very curve I asked you to picture earlier, the one with valleys and a dividing hill. The detailed form of that curve is not arbitrary. It is controlled by the way the Higgs field interacts with itself and with other particles, especially the heaviest ones, and the top quark is by far the heaviest. The strength of the Higgs field's self-interaction is captured by a single quantity that physicists track, and the key fact about that quantity is that it is not constant. It changes depending on the energy scale at which you probe it. This is one of the deep features of quantum field theory. The numbers that describe nature are not fixed dials. They drift as you zoom in, following equations that the standard model lays out precisely. So physicists took the measured mass of the Higgs and the measured mass of the top quark, fed them into those equations, and asked what happens to the strength of the Higgs field's self-interaction as you follow it up to higher and higher energies, which is the same as asking about the shape of the energy curve very far from where we sit. The answer is the heart of the matter. As you climb to enormous energies around 10 billion to 100 billion times the natural unit, the self-interaction strength does not stay positive. It drifts downward, and it crosses zero, and it goes slightly negative. And a self-interaction that goes negative at high field values means precisely one thing for the shape of the curve. Far from our comfortable hollow, the ground turns and heads back downward. There is a deeper valley out there. Our vacuum is not the true bottom. It is a false vacuum, exactly the kind Coleman wrote the death of. I want to be careful and precise here, because this is the crux, and it is easy to overstate. The standard model, taken at face value, with the measured Higgs and top masses plugged in, says our vacuum is metastable. Metastable is a specific and important word. It does not mean stable, and it does not mean unstable. It means stable for now, stable against any ordinary disturbance, sitting quietly in its hollow, but not the true lowest state, with a deeper valley reachable, in principle, by quantum tunneling, over timescales we will come to. The ball is in the higher valley. It is resting. It is not going anywhere on a human timescale, but it is not at the true bottom, and the path to the true bottom, however long it takes, is open. The physicists who worked this out did not bury the result. They named it with a phrase that has stuck. They said the universe is near critical, and they described our situation as living on the edge. A series of careful papers by Giuseppe de Grassi and his collaborators, and then by a larger group whose lead authors include Dario Buttazzo and Gian Giudice and Alessandro Strumia, mapped out exactly where our measured numbers fall on the chart of possibilities. The chart has regions. There is a region where the vacuum would be absolutely stable, the true bottom, safe forever. There is a region where it would be unstable, doomed quickly, which we can rule out because we are still here. And between them there is a narrow strip labelled metastable. When you mark the point set by the real Higgs and real top quark masses, it does not land comfortably in the middle of the stable region, where you might hope. It lands in that thin metastable strip, and astonishingly close to the very boundary line between stable and metastable. Sit with how strange that is, because the strangeness is, to many physicists, the most interesting part of the whole subject. The two masses could have been anything. There is no known law that fixes them at the values they have. They could have placed us deep in the safe region, or deep in the doomed region. Instead, out of all the places the point could have fallen, it fell almost exactly on the seam, in the narrow band where the vacuum is metastable but only just, perched at the dividing line as if balanced there on purpose. Nobody can yet say why. It might be a meaningless accident. It might be a clue, a fingerprint left by physics we have not yet discovered, some deeper rule that nudges the numbers to the edge for reasons we cannot read. The near criticality of the universe is right now an unexplained fact sitting in plain sight, and we will come back to it at the very end because it may be the real mystery hiding behind the dramatic one. But notice what has happened in this part, and let it land gently rather than sharply, because there is no need for alarm. For 30 years, vacuum decay was a rigorous theory that might have had nothing to do with us. Then 2 particle masses were measured, and when you put them into the equations the standard model itself provides, they pointed at the metastable strip. The door Coleman described stopped being a door in some other universe. It became, apparently, a door in our house. We did not choose to find this. We were looking for the Higgs boson, celebrating the completion of a beautiful theory, and the same numbers that confirmed our understanding of mass also whispered that the ground we stand on is a hollow, not the bottom. There is a human texture to this discovery that I do not want to pass over because it changes how the result feels. The physicists who calculated our position on that chart were not trying to deliver bad news. They were doing something physicists love, which is taking a freshly measured number and following it as far as the equations will carry them, to see what it implies about parts of nature we cannot reach directly. The Higgs mass was a gift, the final missing piece of a theory a century in the making, and the natural next move was to ask what that piece, combined with the others, said about the world at the highest energies. The metastability verdict fell out of that honest curiosity, almost as a side effect. No one set out to learn that the vacuum might be false. They set out to understand the particle they had found, and the understanding came with a quiet, uninvited implication attached, the way a clear answer to one question so often opens a stranger one behind it. And still, and I cannot stress this enough, none of this means the end is near in any ordinary sense of the word. Metastable means stable for now, and the for now turns out to be enormous, longer than the age of the universe by a margin that beggars the imagination. We are about to look at exactly how long, and the answer is so vast that it should reassure you completely. But there is a twist hidden inside that reassurance, a twist about the difference between a long average and a fixed appointment, and it is the twist that gives this whole episode its title. Before we get to the comfort, though, I want to take you to the edge itself, to the shape of the curve we are perched on, and let you stand at it for a moment, because feeling where we are is different from being told. Let us walk out to the edge. Part 6. Living on the Edge. I want to take you somewhere now that does not exist as a place, but that physicists carry in their minds whenever they think about this problem. I want to take you to the shape of the Higgs field's energy, the curve we have been describing, and let you stand on it as if it were real terrain you could walk. This is a thought experiment, a way of seeing, and I am going to ask you to imagine it slowly, because the whole point of standing on the edge is to feel where the edge is. So close your eyes, in your mind at least, and shrink yourself out of the ordinary world entirely. Leave behind the room you are in. Leave behind atoms and stars. Step into the abstract space where the only thing that exists is the value of the Higgs field, drawn out as a smooth rolling curve with height standing for energy. You are standing in a valley. The floor under your feet is wide and almost perfectly flat, and it has felt flat for as long as anything has existed. This is our vacuum. This is the value the Higgs field holds in every empty patch of space across the entire observable universe, the value that lets your atoms be atoms. Walk a little. The ground barely changes. In every direction you have ever been able to probe, with every experiment ever performed, the floor stays level and the valley holds you, and it is the most natural thing in the world to believe you are standing on the bottom of everything. Now walk in one particular direction, the direction of higher and higher field values, the direction that corresponds to those enormous energies the physicists followed in their equations. At first nothing changes. The floor stays flat. You walk for what feels like a very long way, and then, far out, so far that no experiment we can build will ever take us there directly, the ground begins, almost imperceptibly, to rise. You're coming to the dividing hill. It is gentle at first, then steeper. If you could climb it, you would reach a crest, and from the crest you would see, for the first time, what has been hidden from the valley floor your whole existence. On the far side, the ground does not level out into more of the same. It turns downward. It falls away into a deeper valley, lower than the one you have always called home, and it keeps falling further down than you can see. That deeper valley is the true vacuum. That is the bottom Coleman wrote about, and the hill between you and it is the barrier, the thing quantum tunneling can pass through. Standing here, on the rim where the flat floor first begins to climb, you can finally feel the truth that the measurement of 2012 delivered. We do not live deep in a safe basin with high walls on every side. We live in a hollow whose dividing hill is, in the relevant sense, not far away and not especially high. The numbers that came out of Geneva placed us right here, near the edge of the safe ground, a short walk in field space from the slope that leads down to somewhere else. Open your eyes again. That is what physicists mean when they say the universe is near critical, when they say we are living on the edge. It is not poetry. It is the literal placement of our measured numbers on that curve. We are close to the seam between a world where the floor rises forever in every direction, an absolutely stable vacuum that could never decay, and a world where the floor turns over into a deeper valley not far out. And we landed on the second kind, just barely, in the thin metastable band, near enough to the boundary that a small change in the numbers would have put us on the safe side instead. Here is what genuinely unsettles the people who study this, and it is worth saying plainly because it is the honest centre of the science. Nobody knows why we're perched here. There is no accepted reason. The masses of the Higgs and the top quark, the two numbers that set our position on the curve, are not predicted by any theory we have. We measure them, we do not derive them, and out of the entire range of values they could have taken, they took values that put us almost exactly on the edge. If the top quark were a little lighter, we might be in the absolutely stable region, the true bottom, safe beyond question. If it were a little heavier, we would be deeper into the metastable strip, or even into the unstable region we know we cannot be in because we still exist. Instead, we sit on the seam, balanced, near critical, for reasons no one can give. This is the kind of fact that pulls in two directions at once, and I think it is worth feeling both pulls rather than collapsing into either. On one side, it might mean nothing. The universe is under no obligation to make its numbers comfortable for us, and a value that happens to land near a boundary is not, by itself, evidence of anything but chance. Boundaries exist, and numbers have to fall somewhere, and sometimes they fall close to a line. On the other side, physicists have learned, again and again, that when a quantity sits suspiciously close to a special value, it is often trying to tell them something. A coincidence that's sharp can be the visible edge of a hidden law. The near criticality of the Higgs might be a clue that there is physics beyond the standard model, some deeper structure that pins the numbers near the edge for a reason we have not yet learned to read. We do not know which it is. That not knowing is genuine, and it is one of the open questions that makes this more than a scary story. There is also a sharp, practical caveat tucked inside all of this. An intellectual honesty demands I put it on the table rather than hide it for the sake of drama. The exact location of the boundary, the precise line between stable and metastable, depends very sensitively on the mass of the top quark, and the top quark's mass is, as these things go, hard to measure with perfect precision. There is a real uncertainty on it, a small range rather than a single exact figure. Shift the top quark's mass within that range and our point on the chart slides toward the safe side or further into the metastable band, which means our verdict on the ultimate fate of the vacuum currently rests, in part on a number we have not fully nailed down. The conclusion that we live in a metastable vacuum is robust enough to take seriously, but it is not carved in stone. It is a reading, with error bars, of an extrapolation that assumes the known physics holds all the way up to energies we have never tested. That is the truthful shape of what we know. It is worth understanding just how finely the chart is divided, because the word edge can sound vague until you see the shape of it. Imagine the chart the physicists drew, with the mass of the top quark running along one direction and the mass of the Higgs running along the other. Across that chart they mapped 3 territories. There is a large region where the vacuum would be absolutely stable, the floor rising forever, no deeper valley anywhere, safe beyond any question. There is another region where the vacuum would be unstable, doomed so quickly that a universe born there could not have lasted as long as ours has, which is how we know for certain we're not in it. And between those 2 territories runs a narrow border zone, the metastable strip, where the vacuum is stable for now but not at the true bottom. When you place the single point marked by our real, measured masses, it does not sit in the safe interior. It sits in that thin border strip and not in the middle of it, but close to the very line where stable becomes metastable. That is the edge. It is not a metaphor for danger. It is a literal position on a real chart, and we landed almost on the seam. I keep returning to the fact that nobody knows why, because I do not want to smooth it over into something tidier than it is. In a universe with no preferences, the 2 masses could have fallen anywhere across that whole chart. There was no rule pulling them toward the boundary, and yet there they are, perched on it. When physicists encounter a coincidence that precise, their instinct, trained by a century of discoveries, is to suspect that it is not a coincidence at all, that some deeper principle they have not yet found is responsible for the placement. But instinct is not proof, and it remains entirely possible that the position is simply where the dice landed, meaningful to us only because we are the ones reading the chart. Both possibilities are alive. The edge is real, the reason for it is unknown, and that unknown is, to many of the people who think hardest about this, the most tantalizing part of the whole subject. So where does that leave us as we stand here on the rim, looking at the slope that leads down to the deeper valley? It leaves us with a strange and specific kind of knowledge. We know there is a way down. We know, from Coleman and from DeLucia, exactly what would happen if even a single patch of space ever took it. And we know, from the measurement of 2012, that we appear to be standing close enough to the edge that the way down is genuinely open to us, not just to some imagined other cosmos. What we have not yet done is watch it happen. We have not yet followed a single bubble from the instant it tunnels into being, and that is where we go now to the smallest and most consequential event the universe could ever stage, the birth of a bubble of true vacuum, somewhere out in the dark after a wait longer than the universe is old. Part 7. The bubble is born. Somewhere, in a region of space far from any star, nothing is happening. That is the first thing to understand about how this begins. There is no build-up, no gathering storm, no slow accumulation of pressure that a watchful observer might notice and measure. There is only ordinary empty space, the same metastable vacuum that fills the room around you, sitting quietly in its hollow, as it has done for 13.8 billion years. The fields hold their familiar values. The dividing hill stands between this patch of space and the deeper valley beyond, exactly as it stands everywhere. And then, with no cause that anyone could ever point to in a volume smaller than a single atom, the fields tunnel through. Let me make this moment as real as I can, because it is the hinge of everything, and because it deserves to be seen rather than summarized. Picture that patch of space. It is unremarkable, dark, cold, indistinguishable from the space beside it. Inside it, the Higgs field has held our value since the beginning of time. Now, in an instant with no duration worth naming, by the same quantum chance that lets a particle pass through a wall it cannot climb, the field in this one tiny region slips over to the other side of the hill and settles into the deeper valley. For the briefest moment it is only a speck, a microscopic seed of a different reality, and it teeters on Coleman's knife edge between collapsing back into nothing and beginning to grow. Most such seeds, across the long history of the cosmos, have collapsed. This one does not. It has tunneled into being already larger than the critical size, and so the balance tips the other way. The energy stored in the false vacuum around it floods toward the seed, the wall takes hold, and the bubble begins to open. Within a span of time too short to picture, the wall is moving outward at very nearly the speed of light, a perfect expanding sphere of rewritten reality, silent and dark, gaining radius every instant and then gaining it faster. There is no sound, because sound cannot exist in the thing it is becoming. There is no flash, because the wall outruns its own light. There is only a sphere of somewhere else growing. That is the birth. Now let me pull back and tell you what it means in slower, plainer terms, because the immensity of it hides inside how undramatic the start truly is. The first thing to absorb is that the trigger is nothing. There is no trigger. We are so used to catastrophes having causes, an asteroid, a spark, a fault line slipping, that the mind reaches automatically for what set this off, and the honest answer is that nothing set it off. Quantum tunneling does not require a cause in the way everyday events do. It is a spontaneous process, governed by probability alone. The fields in any patch of false vacuum have, at every moment, a tiny chance of tunneling, and that chance does not depend on anything having been done to them. No one has to heat the space, or strike it, or disturb it. It simply has, forever, a faint probability of slipping, the way a single radioactive atom has a chance of decaying at any instant without anything happening to it. The bubble is not unleashed, it is not provoked, it just, at last, occurs. The second thing to absorb is the speed, and what the speed forbids. The wall reaches nearly the speed of light almost immediately and holds there, because nothing slows it. In ordinary explosions, the blast wave pushes against the air, loses energy, and fades. This wall pushes against nothing it cannot convert, and every bit of space it converts feeds it more energy, so it never tires and never slows. It moves at the cosmic speed limit, the same speed as light, the same speed as every signal, every influence, every possible carrier of information in the universe. And that fact has a consequence so important that I planted it earlier and have been waiting to harvest it. Nothing can arrive ahead of the wall to warn of the wall, because nothing travels faster than the wall. The light from the region it has already swallowed, if any escaped, would arrive at the same instant the wall itself arrives, because they move together. You cannot see it coming, not because it is too fast for human reflexes, though it is, but because of something deeper. The fastest possible warning and the thing itself are the same front, travelling side by side, and they reach you together or not at all. The third thing to absorb is what the bubble does as it passes. The wall is the boundary between our vacuum and the true one, and as it sweeps over a region, it converts that region. The Higgs field there flips to the deeper value, and because so much of how matter works depends on the Higgs value, the consequences are total. The masses of particles change, the balance between the forces shifts, the exquisitely tuned conditions that allow protons to hold together, that allow electrons to orbit, that allow atoms and molecules and chemistry to exist, are simply gone, replaced by a different set of rules under which the structures of ordinary matter cannot survive. A star caught by the wall does not burn or explode in any familiar way. The very possibility of it being a star ends as the wall crosses it, and then, following Coleman and DeLucia, the converted region, with its lower and likely negative vacuum energy, begins to collapse under its own gravity toward a singularity. The wall rewrites, and the gravity finishes. I am aware of how this sounds, and I want to slow the pace and hold something steady for you, because the goal tonight is not dread. Everything I have described is what would happen if a bubble nucleated near enough to reach us. It is a faithful account of the physics, but the key word in that sentence is if, and the deeper truth, which we are building toward carefully, is that the chance of such a bubble forming near us, in any stretch of time that means anything to a living being, is so small that it is almost a category error to worry about it. The mathematics that makes the bubble sound inevitable when you describe its mechanics is the same mathematics that makes its occurrence here, now, fantastically unlikely. We will get to those numbers, and they are genuinely reassuring. I am not hiding a darker truth behind the comfort. The comfort is real, and it is earned. But there is one feature of this event that survives all the reassurance, and it is not about probability at all. It is about character. Every other disaster a person can imagine comes with a relationship to time that we know how to feel. There is a before, in which you sense the thing approaching. There is a during, in which it happens. There is, for those who survive, an after. Our entire emotional vocabulary for catastrophe is built on that structure of before and during and after. The bubble does not have it. For anyone in its path, there is no before, because there is no warning that could have reached them. There is no during that they could perceive, because the rewriting of their atoms and the arrival of the only possible signal of it are the same instant. And there is no after, because there is no them left to have one. The event is total not only in what it destroys, but in the way it relates to time. It removes the very interval in which experience could happen. Let me return for a moment to the inside of that growing sphere, because there is a detail about scale that makes the whole thing easier to picture, and, oddly, easier to make peace with. The wall is not a flat sheet sweeping across a flat world. It is the surface of a sphere, expanding outward in every direction from the point where the bubble was born. In the first second of its life, it would be roughly a light second across, which is to say wide enough to swallow the distance from the Earth to a point well beyond the Moon. In a year, it would be a light year across, large enough to engulf the space around the nearest stars, and it keeps going, the radius growing without pause, sweeping up more volume with every passing moment, so that the longer it has existed, the faster, in raw terms, it consumes. A bubble that had been growing for 1,000,000 years would already be a region 1,000,000 light-years across, larger than many galaxies, and still expanding at the same relentless speed. There is no point at which it slows, no size at which it tires, no boundary at which it stops. Left alone in an ordinary non-expanding space, it would simply grow forever. There is a temptation, when you hear all this, to imagine standing at a safe distance and watching the sphere approach, the way you might watch a storm front cross a plain. I want to take that image away gently, because it is the one thing the physics will not permit, and removing it is the doorway to the strange calm that waits in the next part. you could not watch it approach. There would be no front visible on the horizon, no growing shadow, no light from the converted region arriving early to warn you. The reason is the same speed we keep returning to. The wall moves as fast as light, and so the light that might have shown you the wall travels alongside the wall, never ahead of it. The sphere could be a single second away from the Earth, close enough that in one more heartbeat it would arrive, and every telescope on the planet, every eye turned to the sky, would see nothing unusual at all, the same calm stars, the same quiet dark, right up until there was no longer anyone to see. That is a strange thing to carry, and we are going to look straight at it in the next part, because it is the true centre of this whole subject, the place where the science turns into something almost philosophical. The bubble, racing outward at the speed of light, carries a peculiar gift hidden inside its terror. It is the one ending that no one could ever experience as an ending, and once you understand why, the fear that the idea first provokes begins, quietly, to come apart in your hands. So let us go to the heart of it, to the simple, vertiginous fact that you would never see it coming, and to what that fact really means. Part 8. You would never see it coming. There is a sentence I have used a few times now, almost in passing, and I have done that on purpose because I wanted it to feel ordinary before we looked at it closely. The sentence is, you would never see it coming. We say something like it all the time about sudden misfortunes, and we usually mean it loosely, that the thing arrived faster than we expected, that it caught us off guard. When physicists say it about vacuum decay, they do not mean it loosely. They mean it in the strictest, most literal, most absolute sense the universe allows, and understanding exactly how literal it is changes the feeling of the whole idea. Start with the plain physics, which you already have in your hands. The bubble wall moves at essentially the speed of light. Light is the fastest thing there is, and more than that, it is the carrier of seeing itself. When you look at anything, a star, a face, this very moment, you are receiving light that travelled from the thing to your eyes. You never see the present. You always see the past, the light that left a moment ago or years ago or billions of years ago for the most distant objects. Vision is always a message from the past, delivered at the speed of light. Now ask what it would take to see the bubble coming. You would need light from the bubble, or from the region it had already swallowed, to reach your eyes before the bubble itself reached you. But the bubble travels at the same speed as that light. The light and the wall move together, neck and neck, a single front. The message and the messenger are the same object, so the warning cannot arrive first, not because our instruments are too slow, not because the event is too sudden for human reaction, but because the laws of the universe forbid any signal from outrunning the thing it would be warning you about. This is the part that I think deserves real stillness, because it is genuinely unlike anything else we ever face. With an asteroid, telescopes can spot it years out. With a tidal wave, there are minutes or hours. With a heart attack, there can be a flicker of warning. Even the heat death of the universe, slow and total, announces itself across unimaginable stretches of time. The bubble announces itself never. The instant you could know is the instant it is already here, which is to say, there is no instant in which you could know at all. Let me hold that still for one more turn, because it is the emotional centre of everything tonight, and I want it to land softly rather than sharply. The thing that could end everything arrives at the exact same moment as the only signal that it is coming. There is no gap between the warning and the event, not a small gap, not a fast gap, but no gap whatsoever. And inside that fact is something that surprises almost everyone the first time they truly grasp it. If there is no interval in which you could know, then there is no interval in which you could be afraid. Fear needs time. Dread needs a before. To be frightened of a thing, you have to know it is coming, and there has to be a stretch, however brief, between the knowing and the arrival, in which the fear can live. The bubble erases that stretch. It does not give you a terrifying final moment. It gives you no final moment at all, because the ending and any awareness of the ending are the same instant, which means there is, functionally, no awareness of it ever. This is why I've been calling it, since the very beginning, the quietest apocalypse. I asked you then to hold that phrase loosely, because its meaning would change, and here is where it changes. When you first hear quietest apocalypse, it sounds like a horror, a doom that creeps up in silence and takes you unaware, and that reading carries fear. But the deeper you go, the more the quiet turns out to mean something else entirely. It is not the quiet of a predator in the dark. It is the quiet of an event that cannot be perceived by anyone, ever, even in principle. There is no scream because there is no time to scream. There is no terror because there is no before in which to feel it. The apocalypse is quiet in the most complete way imaginable. It would pass over the entire earth, over every person, in far less time than a single nerve impulse takes to travel, and not one of those people would experience a single instant of it. They would simply, mid-sentence, mid-breath, mid-thought, no longer be, and there would be no them remaining to notice the interruption. I find, and many physicists quietly admit they find, that this drains the fear out of the idea rather than feeding it. We fear endings because we imagine experiencing them, the awareness, the loss, the final moment of knowing. This ending offers none of that to be experienced. It is, in a strange way, the gentlest possible death for a universe, precisely because it is the most total. Nothing suffers it. Nothing endures it. Nothing is left behind to grieve. The very completeness that makes it sound like the worst of all endings is the same completeness that makes it impossible to dread from the inside. You cannot fear a thing you could never feel. There is even a kind of peace available here, if you are willing to sit with it, and it is not a trick or a consolation prize. Consider how most of our fear about mortality, at every scale, is really fear of the runway, the seeing it come, the helpless interval of knowing. The bubble removes the runway entirely. It is the one catastrophe with no anticipation built into it. And while I would never pretend that makes it desirable, I think it genuinely makes it less frightening than the slow endings we more easily accept. The heat death, with its long cold fading, at least could be watched by something. The bubble could be watched by nothing. It asks for no bravery, because there is no moment in which bravery would be called for. It is, of all the universe's endings, the only one you have my full permission to stop worrying about, not because it cannot happen, but because if it did, there would be nothing it could do to you that you would ever know. And yet, having drained the fear, I do not want to leave you with the impression that the idea is therefore empty, that we have explained it away into nothing. Quite the opposite. What remains, once the fear is gone, is the more interesting feeling, the one I promised at the start. It is a kind of vertigo, calm rather than panicked, about how much we took for granted. We assumed the flaw under reality was permanent. We assumed empty space was the one thing that could never fail. And the physics has quietly informed us that this is an assumption, not a guarantee, that the most reliable seeming thing in existence may be resting in a hollow rather than standing on bedrock. That realization does not require fear. It requires only honesty and a willingness to feel the strangeness of being told that forever was never actually promised. I think it is worth comparing this, carefully, to the way we usually think about death and endings, because the comparison is where the unusual comfort really comes from. Almost everything we fear partly through anticipation. The dread of an illness is largely the dread of the time spent knowing. The fear of a fall is the fear of the moment in the air. Even our stories about the end of the world are really stories about the watching of it, the gathering clouds, the last days, the chance to say goodbye, the awful interval of awareness. We rehearse these things in our minds, and the rehearsal is itself a large part of the suffering. What makes vacuum decay so unlike all of that is that it offers nothing to rehearse. There is no last day, because there is no day on which you would know. There is no goodbye, because there is no interval in which to say it. The event does not include a period of awareness for the simple reason that awareness, like everything else, travels no faster than light, and the wall has already claimed that speed for itself. I do not offer that as something grim. I offer it as something that, looked at honestly and without flinching, lifts a weight rather than adding one. The endings we are taught to fear are the ones with a runway, and we fear them in large part because we picture ourselves on that runway, watching. This ending has no runway at all. If it ever came, you would not be on a runway watching it approach. You would simply be here, in this ordinary moment, with the stars in their familiar places and the night quiet around you, and then the sentence of the universe would continue without you, and the absence of you would not be a thing you experienced, because experience requires a before and an after, and this event provides neither. It is, in the most literal sense available in physics, an ending that contains no ending for anyone to undergo. The quietest apocalypse takes nothing from you that you could ever feel it taking. But all of this, the no warning, the calm at the centre of the terror, has been about the character of the event if it happens. It has not yet touched the question you have surely been holding through all of it. The question that decides whether any of this is a practical concern or a beautiful abstraction. How likely is it? When might it happen? Is the clock ticking down towards some hidden hour, or is there no clock at all? The answer to that question is the most reassuring part of the entire subject, and also the most quietly mind-bending, because it turns out that a thing can be almost infinitely unlikely to happen soon, and yet have no schedule whatsoever, no countdown, no due date. To understand how both of those can be true at once is to understand the title of this whole piece. So let us look at the clock, the one with no hands. Part 9. The clock with no hands. Here is the question that decides whether everything we have discussed is a real concern or a beautiful piece of mathematics with no claim on your evening. How long until it happens? And the answer comes in two halves that seem, at first, to contradict each other, and learning that they do not contradict, that they are two faces of the same coin, is the single most important idea in this whole subject. It is also the idea hidden in the title. The first half of the answer is enormously, almost comically reassuring. Physicists have estimated how long our metastable vacuum should be expected to last before it decays, and the numbers are so large that they break the ordinary meaning of the word soon. The estimates vary because the calculation is difficult and sensitive to the same uncertainties we discussed, but they all land in the same impossible territory. One careful calculation by the physicists Anders Andreasen, William Frost and Matthew Schwartz, published in 2017, put the expected lifetime at around 10 to the power of 139 years. Let me try to make that number mean something, though it resists meaning. It is a 1 followed by 139 zeros. The universe right now is about 13.8 billion years old, which is roughly a 1 followed by 10 zeros. The difference between those two numbers is not a difference you can feel. The age of the universe set beside the expected lifetime of the vacuum is so small that it effectively rounds to zero. Other estimates in the scientific literature range across an enormous span, from something like 10 to the 100th power years up to 10 to the 500th power years and beyond. But every single one of them is vastly, unfathomably longer than the entire history of the cosmos so far. So on the first half of the answer, you should feel completely at ease, and I mean that without any hidden caveat. By every calculation we can make, the vacuum is expected to last for a length of time next to which the age of the universe is nothing. If the only thing you take from tonight is a number, take that one. We are, in expectation, safe for so long that no human concern, no civilizational concern, no concern about the Earth or the Sun or the galaxy, comes anywhere near it. The Sun will swell and die in a few billion years, the stars will burn out over far longer spans, and still, all of that will play out comfortably inside the period during which the vacuum is overwhelmingly likely to remain exactly as it is. On any timescale you could ever care about, vacuum decay is not going to happen. Now the second half of the answer, which does not undo the first but stands beside it, strange and quiet. A long expected lifetime is not a countdown. It is not a due date. It does not mean the universe is aging toward an appointment that draws closer with each passing year. And the reason cuts to the heart of how quantum probability works. Quantum tunneling is what physicists call memoryless. The chance that the vacuum decays in the next second does not depend at all on how long it has already survived. It does not build up over time. It does not get more likely as the eons pass. It is the same tiny probability now as it was a billion years ago, and the same as it will be a billion years from now. The vacuum is not a fuse burning down. It does not remember how long it has lasted, and it is not owed a decay for having lasted so long. The right picture is not a clock counting down to a fixed hour. The right picture is a coin, an absurdly weighted coin, being flipped over and over everywhere all the time. In every region of space at every instant, the universe is in effect flipping this coin, and the coin almost always comes up the same way. No decay, no decay, no decay, for 13.8 billion years and counting. The chance of any single flip coming up the other way, decay, is so staggeringly small that the expected wait for it is that monstrous number we just discussed. But here is the thing about a coin like that. Because the flips are memoryless, the next flip is always just a flip. It does not know how many have come before. The chance it comes up decay in the very next instant is tiny, but it is not zero, and it is exactly the same tiny number it has always been. There is no moment when the coin is more likely to turn. There is no hour the universe is counting toward. There is only the endless flipping and the constant, unchanging, almost vanishing chance. It helps to hear the sighs of these lifetimes spoken slowly, because the speed of the words usually hides their meaning. A 1 followed by 139 zeros is not merely a long time, it is a length of time so far beyond the lifespan of stars that the entire era in which the universe contains shining stars at all, which itself stretches to a 1 followed by 14 zeros years, would have come and gone more than 100 times over before you even approached it. The black holes would have formed, swelled, and evaporated. The last light would have faded ages before, and still the expected wait for the vacuum to decay would stretch on, almost untouched, into a darkness so deep that the word late loses all meaning. When physicists hand you a number like that, they are not describing a danger on any horizon you could ever see. They are describing a wait so long that every story the universe will ever tell, every era it will ever pass through, fits inside the early part of it. Do you feel how those two halves fit together now? The expected wait is unimaginably long, and there is no schedule. Those are not intention. They are the same fact seen from two sides. A thing can be almost infinitely unlikely to happen in any given stretch of time, and at the very same time have no fixed date, no countdown, no place on the calendar at all, so that it is never any nearer or any further than it ever was. The vacuum is not due to decay in 10 to the 139 years. That is just the average wait implied by how rare each flip is. The actual decay, if it ever comes, is not scheduled for then or for any other time. It could come in 1 trillion years. It could, with the same tiny probability it has always had, come in the next second. Both are allowed. Neither is owed. And that, finally, is what the title means. Why is the end of the universe far closer than you think? Not because it is likely soon. It is overwhelmingly unlikely soon, and you should sleep easily on that. It is closer than you think in a different and stranger sense. Every other ending sits at a fixed, distant point on the timeline, a place you're slowly travelling toward, with the whole long road still ahead of you. This ending has no fixed point. It is not waiting at the far end of a road. It is, in a sense, equidistant from every moment, including this one, because the chance of it has nothing to do with when you happen to be standing. It is not 10 to the 139 years away. It is no particular distance away at all. And a thing with no distance, a thing that could in principle be touching the present moment with the same small chance it touches any moment, is, in that peculiar accounting, closer than the comfortably scheduled doom you imagined. Not nearer in expectation, nearer in kind. It has shed the one thing that made the other endings feel safely far, which is their place on the calendar. I want to be the careful narrator here and make sure the reassurance and the strangeness stay properly balanced, because it would be easy to tip too far either way. The strangeness is real. There is no countdown, and the possibility genuinely attaches to every instant equally. But the reassurance is also real, and it is the larger fact. The chance per instant is so close to nothing that, over the entire age of the universe so far, it has not happened once, anywhere we can see, and the expected wait dwarfs all the time there has ever been. To lie awake over vacuum decay would be like lying awake over the chance that every atom in your body will, by quantum tunneling, simultaneously leap one step to the left, which is also allowed by the laws of physics and also so unlikely that it will, in practice, never occur. The honest emotional response to the clock with no hands is not fear. It is wonder, the particular wonder of holding two true things at once and feeling your sense of solid time go gently transparent. The single radioactive atom is the cleanest way I know to make the memoryless idea feel true rather than merely stated, so let me draw it out. Take an atom of a radioactive element, one that will eventually decay by emitting a particle. You cannot predict when it will decay. You can only say that in any given stretch of time it has a certain chance of doing so. Now here is the part that surprises people. Suppose the atom has already sat there, undecayed, for 1 billion years. Is it now more likely to decay soon, as if it were overdue? It is not. Its chance of decaying in the next moment is exactly the same as it was on the first day. The atom does not age in the way we age. It does not accumulate a pressure to decay. It does not remember how long it has waited, and it is owed nothing for its patience. Each moment, it simply faces the same small chance, fresh, as if the whole long wait had never happened. The vacuum of the universe is like that atom, scaled up to the size of everything, with a chance so much smaller that the expected wait stretches past every number we have names for. This is why the language of a countdown is so misleading, and why I've been careful to avoid it. A countdown implies a fixed endpoint that draws nearer as time passes, the way the hands of a clock close on midnight. But the vacuum has no midnight. There is no hour it is approaching. If you could somehow watch the universe for 1 trillion years and find it undecayed, you would not be 1 trillion years closer to the decay. You would be in exactly the same position you are now, facing the same unchanged, almost vanishing chance in the next instant. The decay is not at the end of a road we're travelling. It is a possibility that hovers, equally faint, over every moment that has ever been or will ever be, and that is a genuinely different way for a thing to relate to time than anything in ordinary life, where almost everything either grows more likely as it ripens or less likely as its window closes. The vacuum's chance neither ripens nor closes. It simply, eternally, is. There remain 2 questions, though, that the probability alone does not settle, and they are the ones people ask the moment they first hear about all this. The first is whether we could cause it ourselves, whether something we build, some experiment, some collision, might give the universe a fatal nudge. The second is whether, even without our help, a bubble might already exist somewhere out in the dark, born long ago, racing toward us right now beneath our notice. Both questions have real answers, and the answers are, on balance, comforting, though one of them comes with a beautiful and humbling twist. So let us turn to them and ask whether the universe has ever come close, and whether we could ever push it over the edge ourselves. Part 10. Could we cause it, and could it already be here? When people first learn about vacuum decay, the fear that arrives fastest is not about deep time, it is about us. We build machines that smash particles together at tremendous energies. We are deliberately recreating in tiny volumes conditions more extreme than anything the everyday world contains. So the worry forms almost on its own. What if one of those collisions in one of those machines gives the false vacuum the nudge it needs? What if we, in our curiosity, are the ones who tip the ball over the hill? This fear reached its loudest pitch around the year 2008, when the Large Hadron Collider, the very machine that would later find the Higgs, was about to switch on, and a scattering of voices warned that it might accidentally end the world. The answer to that fear is one of the most quietly elegant arguments in all of physics, and it was worked out years before the machine was even built in 1983 by 2 physicists named Piet Hutt and Martin Rees. Their reasoning does not require you to trust the engineers or to believe any particular claim about how safe a given collider is. It requires only that you look up. Space is full of particles moving at enormous energies, called cosmic rays. Some of them carry energies far, far beyond anything our largest machines can produce. Energies that dwarf the collisions inside the Large Hadron Collider by huge factors. These cosmic rays are not rare visitors. They have been raining down on everything in the universe for billions of years. They strike the Earth's upper atmosphere constantly. They strike the Moon, which has no atmosphere to shield it, directly on its bare surface. They strike the Sun, the planets, and every star and rock across the entire cosmos, ceaselessly, since long before the Earth existed. Now follow the logic, because it is airtight in its simple way. If a high-energy particle collision could trigger vacuum decay, then the universe has been running that experiment, on a scale and at energies we could never match, continuously, for billions of years, in an almost unimaginable number of places. Every cosmic ray striking the Moon is a collision more violent than anything we can engineer. There have been more such collisions in the history of the cosmos than we have words to count, and the vacuum has not decayed. We are still here, the stars are still shining, the universe still runs on the same rules it always has. The continued existence of everything is itself the result of that experiment, repeated beyond measure, always coming back the same way. If nature, throwing energies we cannot approach across billions of years, has never once nudged the vacuum over the edge, then our comparatively gentle machines, working far below those energies, cannot do it either. The collider is safe, and we knew it was safe before we turned it on, not because we trusted ourselves, but because the universe had already run the test for us, untold times, and passed. I want to let that sit as its own small scene. because it is worth seeing rather than just concluding. Picture the moon hanging there, its grey surface bare to space, as it has been for more than 4 billion years. Every second, particles from deep space slam into that surface at energies no human machine has ever reached, each one a tiny experiment in whether the vacuum can be broken. Picture the upper edge of Earth's atmosphere, where the same bombardment flares constantly, a thin shell of collisions far fiercer than anything at Geneva. Picture this happening not just here but on every world, around every star, across the whole reach of the observable universe, and not for a moment, but for the entire age of time. Roll the dice, the universe says, and it has been rolling them, trillions upon trillions of times, in every corner of the sky since before there was an Earth to stand on, and every single roll has come up the same. No decay, no decay, an unbroken streak as long as the universe itself. That streak is the most reassuring fact in this entire subject, and it cost us nothing to obtain. It was always there, written in the simple fact that the sky is still above us. There is a second worry, subtler than the first, and it is the one that does not fully go away, though it shrinks down to something small and honest. Forget about us causing it. What if a bubble has already formed somewhere on its own, by pure quantum chance, long ago and far away, and is even now expanding toward us at the speed of light, invisible because, as we have learned, nothing could announce it ahead of itself? Could the end already be on its way, unseen? The honest answer has two parts, and the first part is yes. In principle, this is possible, and we would not be able to see it. There is no instrument that could detect an approaching wall, because the wall and its light arrive together. If one were coming, the first we would know of it would be the same instant it was already here, which is to say we would never know. But the second part of the answer is where the reassurance returns, and it comes from a feature of the universe we have explored on this channel before, the accelerating expansion of space. The universe is not static. Distant regions are rushing away from us, carried apart by the expansion of space itself, and the most distant regions are receding so quickly that light leaving them now will never reach us. There is a horizon, a boundary beyond which events are forever cut off from us, not because they are too far in simple distance, but because the space in between is growing faster than light can cross it. Any bubble that nucleates beyond that horizon can never catch us, no matter how fast its wall travels, because the space between us and it is expanding faster than the wall can close the gap. The expansion, which on other nights we have discussed as a kind of cosmic isolation, here becomes a kind of shield. The overwhelming majority of the universe is simply too far in this expanding sense to ever threaten us. We are at risk only from bubbles born close enough that the wall could outrun the expansion and reach us, and that is a far, far smaller region than the whole cosmos. The danger does not vanish, but it shrinks dramatically, walled off by the same expansion that carries the distant galaxies forever out of reach. So put the two answers together and feel the shape of the reassurance, which is real and earned and not a sleight of hand. We cannot cause it, because nature has tested the vacuum at energies beyond our reach, countless times, for billions of years, and it has held. And while a bubble could in principle already be travelling toward us unseen, the expansion of space means that almost all of the universe is too far away to ever send one that could arrive, leaving only a comparatively tiny neighbourhood from which a threat could even come, and within that neighbourhood the per-moment chance is the same vanishing number we have marvelled at all along. The picture that emerges is not one of a sword hanging over us. It is one of a possibility so hemmed in by the structure of the cosmos, so rare in time and so limited in reach, that it sits at the very edge of meaningful concern, fascinating to contemplate and almost impossible to fear once you see it clearly. I find it worth dwelling on just how lopsided the cosmic ray argument really is, because once you see the size of the mismatch, the fear of human machines stops being able to stand up. The collisions inside our most powerful collider reach energies of a certain magnitude, and that magnitude, while staggering by the standards of a laboratory, is modest compared to what space provides for free. The most energetic cosmic rays ever detected carry energies tens of millions of times beyond anything our machines produce, and they are not gentle outliers, but a real, recurring part of the radiation that fills the cosmos. When one of those strikes a stationary particle in the upper atmosphere or on the bare rock of the moon, the collision is more violent than anything we could engineer if we covered the Earth in colliders, and these strikes are not occasional. Across the surface of the moon alone, over its 4.5 billion years, The number of such collisions is so large that writing it out would take a line of zeros. Every one of them was a test. Every one of them came back the same. The vacuum held. Stretch that picture across the whole observable universe and the conclusion becomes overwhelming. There are something like 2 trillion galaxies within our view, each holding hundreds of billions of stars, each star bathing its neighborhood in the same relentless rain of high-energy particles, and all of it running continuously for the entire age of the cosmos. The number of natural collisions at energies beyond our reach, summed across all that space and all that time, is so enormous that our own contribution, every collision in every machine we have ever built, is less than a single drop added to an ocean that was already full. If any of those collisions could break the vacuum, it would have broken long ago in some distant galaxy billions of years before the Earth formed, and the wall of that ancient bubble would be part of the history of the universe rather than a worry about its future. The fact that we are here, that the sky's intact, that the experiment has run beyond counting and never once failed, is the quiet, total answer to the fear that we might end the world by looking too closely at it. There is one last turn I want to take before we come to rest, and it is the most beautiful one, because it reaches back to the very beginning of the universe rather than forward to its end. The same physics that could, in principle, end our cosmos in a bubble of true vacuum may also be the physics that started it. The false vacuum is not only a possible doorway out, it may have been the doorway in. To see how the switch that could one day turn the lights off may be the very switch that first turned them on, we have to go back, all the way back to the first instant, and to a man named Alan Guth, who, trying to explain why the universe looks the way it does, reached for a decaying false vacuum and found the spark of creation in it. Part 11. The Same Door at Both Ends. In 1981, a young physicist named Alan Guth was wrestling with a set of puzzles about the early universe that had nothing, on their face, to do with the end of anything. He was trying to understand why the cosmos looked so uniform, so smooth, so flat, on the larger scales, when the simplest version of the Big Bang gave no good reason for it. And the answer he arrived at, the idea that would reshape cosmology, leaned on the very thing we have spent this whole time discussing. It leaned on a false vacuum. Guth's proposal, which came to be called inflation, suggested that in its first unimaginably brief moment, the universe was not in its ordinary vacuum at all. It was caught in a false vacuum, a high-energy state, a hollow in the curve much like the one we have pictured, but with an enormous energy stored in it. And a vacuum with that much energy does something dramatic to space. It drives space to expand, not at a steady pace, but explosively, doubling and doubling and doubling in size in a fraction of an instant, blowing a tiny region up to enormous proportions almost instantly. That runaway expansion, that inflation, would smooth the universe out, flatten it, and stretch it to the vast scale we observe, solving all at once the puzzles Guth had started with. And then, crucially, the false vacuum decayed. It dropped out of the high-energy state, the way a false vacuum does, releasing its stored energy as the heat and matter of the early cosmos, and the ordinary expansion of the Big Bang took over from there. I want you to notice what that means, because it is one of the most quietly profound symmetries in all of physics. The decay of a false vacuum, the very process that could one day erase our universe, may be the same kind of process that created it. At the beginning, a false vacuum decayed, and its decay poured out the energy that became everything, the matter, the light, the structure that would eventually become stars and worlds and us. At the end, if our present vacuum is also false, its decay would do the reverse, sweeping the structure away and replacing it with something in which nothing we know could exist. The same door at both ends of the story. The switch that may have turned the lights on is the same kind of switch that could, in mirror image, turn them off. Guth's original version of the idea, it should be said, had a flaw, and the honest history is worth a sentence. In his first model, the false vacuum decayed by forming bubbles, exactly the bubbles we have described, and the problem was that these bubbles would not merge smoothly into a uniform universe. They would leave the cosmos lumpy and broken rather than smooth, a difficulty that became known as the graceful exit problem. Later physicists, including Andre Linde and others, found better versions of inflation that avoided this trouble, in which the field rolls down gently rather than tunneling through bubbles, and those improved models are the ones cosmologists use today. but the lesson at the core survived every revision. False vacuum physics, the physics of fields caught in hollows, and the energy stored there, sits at the foundation of how our universe began. It is not an exotic add-on, it is woven into the origin story, so consider the strange completeness of what we have arrived at. We began by asking how the universe might end, and we found an ending stranger and quieter than all the others, a bubble of true vacuum that could rewrite reality at the speed of light. We followed it through the mathematics of Coleman, through the gravity of Coleman and DeLucia, through the measurement at Geneva that suggested the door is real and in our house. We faced the no-warning truth at its centre, and found, hidden inside the terror, a kind of peace. We weighed the probabilities and found ourselves overwhelmingly safe, threatened by a possibility with no schedule and almost no reach. And now, at the far end, we find that the same physics points back to our beginning, that the process which might end us is kin to the process that made us. The false vacuum is not only how it might stop, it may be how it started. There is an emotional weight to that symmetry, and I think it is the right note to slow down on before we close, because it is not a frightening weight but a humbling one. We tend to imagine creation and destruction as opposites, as forces from different ends of some moral or cosmic spectrum. The false vacuum quietly dissolves that distinction. The same lawful, impersonal process, a field shedding energy as it settles toward a lower state, is both the spark that may have lit the universe and the flame that could one day consume it. There is no malice in it at either end. There is only a field doing what fields do, rolling toward lower ground when the chance arises. Our entire existence on this reading is the brief, bright interval between two settlings, a long pause partway down a hill, lived out in the stretch of time after one false vacuum decayed and perhaps before another one does. I want to sit a little longer with that symmetry, because I think it carries the real emotional centre of this whole story, deeper even than the no-warning idea, and it is a quiet one rather than a frightening one. We are used to imagining that the universe was made by something grand and is threatened by something terrible, two opposite kinds of event at the two ends of time. The false vacuum tells a humbler and stranger tale. The thing that may have made everything, and the thing that could one day unmake it, are not opposites at all. They are the same kind of event, a field settling from a higher state to a lower one, shedding its stored energy as it goes. At the beginning, that settling poured out the energy that became light and matter and eventually worlds and minds. At the end, if it comes, the same kind of settling would gather all of that back into a different state in which none of it could exist. Creation and ending written in the same equation, separated only by which valley the field is falling toward. When you hold that, the fear has nowhere left to stand, and something gentler takes its place. There is no villain in this story. There is no malice, no punishment, no cosmic judgment hidden inside the bubble. There is only a field, obeying the same patient laws it has always obeyed, rolling toward lower ground whenever the rare chance arises. We are not standing in the path of an enemy. We are living inside a pause, a long quiet interval that opened when one false vacuum decayed, and that will close, if it ever does, when another one does, and the whole of human history, every life, every thought, every night spent looking up, fits comfortably inside that single pause with room to spare. To know that is not to be afraid. It is to feel, very precisely, how rare and how lit this interval is, suspended between two settlings, neither of which has any feeling about us at all. And that brings us back at last to the question I set aside several times tonight, promising we would return to it. The question that I think is the real mystery hiding behind the dramatic one. We have learned that our vacuum appears to be metastable, sitting in a hollow with a deeper valley beyond a hill. We have learned that we are perched not deep in the safe region but right at its edge, near critical, balanced on the seam between absolute stability and decay, for reasons no one can explain. Why? Why is the universe poised there, on the edge, rather than safely far from it? Is it a meaningless accident, or is it a message we have not yet learned to read? That question, more than any fear about bubbles or endings, is what keeps physicists genuinely awake, and it is where I want to leave you, standing at the edge, looking down, and wondering what the edge is trying to tell us. Part 12. Why the edge? We have arrived at the quietest place in the whole story, and I want to spend our last while here, not adding more facts, but turning the ones we have until they settle into something you can carry with you into sleep. The dramatic question, the one on the surface, was how the universe could end without warning. We have answered it. The deeper question, the one underneath, is the one I kept setting aside, and it is this. Why are we sitting on the edge at all? Remember what the measurement told us. The masses of the Higgs and the top quark, two numbers no theory predicts, two numbers we can only measure, placed our universe not comfortably inside the region where the vacuum is absolutely stable, and not inside the region where it would already have decayed, but right on the seam between them, in the thin metastable band near critical. A small nudge to either number, and we would be somewhere unremarkable, plainly safe or plainly impossible. Instead, we are balanced at the boundary, as if set there deliberately, and no one can say why. This is not the scary part of the subject. It is the genuinely mysterious part, the part that might someday turn out to matter more than the bubble ever could. There are, broadly, two ways to feel about a coincidence that Sharp and physics has lived with both. The first is to say it means nothing. Numbers have to fall somewhere, and the universe was never required to make ours land in a tidy place. Perhaps we're near the edge for the same reason a thrown dart lands where it lands, with no significance beyond the throw. The second way is to take the coincidence as a clue. Over and over in the history of science, when a quantity has sat suspiciously close to a special value, it has turned out to be the visible edge of a law not yet discovered, a hint that something deeper is arranging things. The near criticality of our vacuum may be exactly that kind of hint, a fingerprint left on our universe by physics that lies beyond everything we currently understand. Physics that pins the numbers to the edge for a reason we have not yet learned to read. We do not know which way it will fall. That honest not knowing is, to me, far more interesting than any certainty would be. And here, at the close, all the threads we have followed come back together and change their meaning, the way the best ideas do when you have lived with them long enough. Think back to the picture we started with, the ball resting in a valley, certain it had found the bottom. We said then that, for all of recorded history, we may have mistaken the valley floor for the bottom of everything. That began as a statement about potential energy, a tidy bit of physics. It returns now as something closer to a statement about the whole human relationship to permanence. We have always treated empty space as the one thing that could not fail, the reliable floor under all our striving and all our stories. The physics has gently informed us that this was an assumption, never a guarantee. The floor we trusted may be a resting place rather than bedrock. We were never actually promised forever. We only assumed it, because the floor had held for so long that holding seemed the same as permanence. And think back to the phrase I asked you to hold loosely at the very beginning, the quietest apocalypse. It sounded at first like the name of a horror, a doom that creeps in unheard. By now it has turned into something almost the opposite. It is quiet not because it sneaks, but because it could never be experienced by anyone, ever. You would never see it coming, and that sentence too has changed under us. It started as a fact about the speed of the light, a cold piece of physics about signals and walls. It ends as a strange consolation. The ending you cannot see coming is also the ending you never have to dread, because dread needs a before, and this one has none. Of all the ways the universe could end, this is the only one with no fear built into it anywhere. The only one that asks nothing of you, not courage, not grief, not even awareness. It would arrive, if it ever arrived, in the one place the mind can never go, the gap with no duration between one moment and the next. So what do you actually do with all of this lying here, the world solid around you? The answer, I think, is almost nothing, and that is the gift of it. You do not need to fear vacuum decay. By every calculation, the vacuum will outlast the stars, outlast the galaxies, outlast every span of time that could ever touch a living thing, by margins that make the age of the universe round to nothing. And the version of it that has no schedule, that attaches its tiny chance to every instant equally, is not a thing to lie awake over, any more than you would lie awake over the vanishingly small chance that the atoms of your body might all leap sideways at once, which the laws also permit and which will, in practice, never happen. The right response to the clock with no hands is not vigilance, it is wonder. What this idea offers in the end is not fear but perspective, the particular perspective this channel is always reaching for. It is the quiet realization that the ground under reality is more interesting and more provisional than we ever assumed, that empty space is not empty and may not be finished, that the same lawful settling of a field which may have lit the universe could one day, with no malice and no warning, let it settle again into something else, We live in the long, bright pause partway down a hill, and the pause has lasted 13.8 billion years, and by every honest estimate it will last almost unimaginably longer. That is not a reason to be afraid. It is a reason to feel, just for a moment before you drift off, how remarkable it is to be here at all, in the interval, on the floor of a valley that has held, under a sky that is still, against every cosmic ray and every passing eon, exactly where it has always been. There is a particular kind of calm that comes from holding two true things at once without forcing them to resolve, and this subject offers it more cleanly than almost any other in physics. The first true thing is that, by every calculation we can make, we are safe for a length of time so vast it empties the word of meaning, safe past the death of the sun, past the burning out of the stars, past spans next to which all of recorded history is less than a single heartbeat. The second true thing is that this safety is not a guarantee written on the calendar, but a probability attached to every passing instant, a chance so small it has never once turned in the entire history of the cosmos, and yet a chance that belongs to this moment as much as to any other. Most people, when they first meet those two statements, feel them as a contradiction and reach to keep one and discard the other. The quieter and truer response is to let them both stand, because they are both real, and to notice that the feeling they produce together is not fear, but a soft astonishment at how the universe is actually built. I think that astonishment is the thing worth keeping from all of this, more than any single number or name. We move through our days standing on what feels like solid ground, trusting without thought that the floor beneath reality is permanent, that empty space is the one thing that could never change. And the physics has gently corrected us, not with a threat but with a fact, that the floor is a resting place rather than a foundation, that the most reliable seeming thing in existence is holding a value it was never required to keep forever. That correction does not need to frighten anyone. It only asks us to trade a false sense of permanence for a true sense of wonder, to understand that the steadiness we have always counted on is itself a kind of quiet miracle, an unbroken stillness stretching back to the beginning of time and, in all likelihood, forward almost without end. The universe has not decayed. Not in 13.8 billion years, not once, not anywhere we can see. The streak is unbroken, and it will, in all likelihood, remain unbroken for longer than the mind can hold. And if it is true that we are balanced on the edge, near critical, poised at the seam for reasons no one yet understands, then perhaps the right way to fall asleep tonight is not to fear the edge, but to be quietly amazed that we're here to stand on it at all, looking down, wondering, safe in the only home that has ever existed for as long as anyone will ever need,